When we're multiplying exponents, for example, if we had x squared times x to the third power, what this means is that I have x times x, that's the expanded form of x squared, times, make a bigger dot here, and then x to the third power, which is x times x times x. When I multiply x by itself 5 times, I get x to the fifth power. And what this means is that the rule is going to be x to the n times x to the m. The answer is going to be x to the n plus m. I'm adding the exponents. Let's take a look at a couple examples. So in this first example, we have x to the 12th power times x to the 7th power. I'm going to write it like this, where I have the 12 plus 7. And that's going to be x to the 19th power. And then over here, x to the 5th times x to the 8th, I just add the exponents, and it's x to the 13th. Now, if we had exponents that were fractional, say I had x to the 1/2 times x to the 3/4, we're still adding the exponents. So in order for me to add fractional exponents, what I would want to do is change the exponents so that they would have the same denominator. So this one would become 2/4. And then when I add them, x to the 2/4 plus 3/4 is 5/4. And you wouldn't change that to be a mixed number. So there's an interesting thing that happens. Now we'll take a look at dividing. So if we're dividing, it's the exact opposite. Since I'll write the product rule up here, so this is x to the n times x to the m is x to the n plus m. I'm adding the exponents. Well, this is for multiplication. For division, it would be x to the n, and if I'll write it as a fraction, x to the m divided by x to the m. This time we'll subtract the exponents, so it'd be x to the n minus m power. And we'll look at a few examples of that. So here in this first one, I have x to the 5th over x to the 3rd. So I'm going to subtract the exponent. So this is x to the 5 minus 3. And the final answer would be x squared. And in this one over here, I would have x to the 4 minus 2, which would also equal x squared. Now, there's an interesting consequence that happens from the quotient part of this. Let's take a look at a special kind of an example, and we'll see why x to the 0 is going to be equal to 1. So as you're aware, any number that I have, if I have 7 over 7, this equals 1. And 8 over 8, well, anytime we have the same number over the same number, it's going to equal 1. So if I have x to the 4th power divided by x to the 4th power, well, our rule says that this would be x to the 4 minus 4, and this would equal x to the 0 power. And the reason why this would equal 1 is because x to the 4th, whatever the number is, divided by x to the 4th, which is the exact same number, just like 7 over 7, would be equal to 1. And this is why, because of this quotient rule, is why whenever we have any number raised to the 0 power, it equals 1. So what we'll do now is I'll mix up some things. So if I have x to the 4th times x to the 2nd power divided by x to the 3rd power, well, I'm mixing both product and quotient rules at the same time. So what I'll do first is I'll do the product rule. So x to the 4th times x squared is x to the 6th. And this is divided by x to the 3rd power. And then we go on to the quotient rule, which says we subtract the exponents. So this would be x to the 6th divided by x to the 3rd is x to the 3rd. I do want to just write out one of the problems here. I'll make up a simple one. So if I have x to the 3rd power divided by x squared, if I write this in expanded forms, just another explanation, take it a little deeper. X times x is the expanded form for x third, and x times x is the expanded form for x squared. So if I come over here and I say that I have 5 times 5 in the top, and I am dividing by 5, I can simplify the fraction as long as this is multiplication and not addition. 5 goes into itself once and 5 goes into itself once. And what I get is 5 in the numerator and I get 1 in the denominator. Well, same thing over here. I have 3 x's in the top, they're all being multiplied, and 2 x's in the bottom. So I'm going to simplify this, and I can say x goes into itself once, x goes into itself once. Then I have another x goes into itself once, and again here. And what I have left is I have a single x over here and a 1 in the denominator. I can just say x to the first power, which is x to the 3 minus 2. So we've covered enough material already that we should be able to do something that looks like this. This is something really for Algebra 1 or possibly linear algebra. I'm going to write the numerator in fully expanded form, and then I'll do the same with the denominator, and then we'll go through and simplify. So 25 is the same as 5 times 5. And x to the 7th, I should have picked something with smaller exponents. So I have 7 x's here, and then I have 3 y's. And then in the denominator, I have one of the 5's, and then there's 3 x's and a single y. Now I can simplify through without using the rules. We'll do it over again using the rules. So 5 goes into itself once, and 5 goes into itself once. So then for the x's, there's 1 x here, 1 here, 1 here, and so on. And then I have one of the y's and one of these y's. And in the denominator, all I have left is a single 1. And in the numerator, I have a 5. And then I have 4 of the x's, so that's x to the 4th. And then I have 2 y's, so that's y squared. I can just write this simply as 5x4 y2. Now, just using our rules, looking over here, 25 divided by 5 is 5. X to the 7th divided by x to the 3rd is x to the 4th. And then I have x to the first power goes into, excuse me, this is y to the first power goes into y cubed 2 times. So goes in y squared times, I should say. And the only thing that's left in the bottom after I simplify this is a 1, so I don't need it to be over 1. This is the same answer, just using the shortcut rules.